Hello, good evening, students. Good evening, students. In last lecture, we had discussed uh, about long columns, and we had discussed about Euler's column theory. Okay, in last lecture, uh, by using Euler's column theory, uh, we had derived uh, formula equations for the buckling or crippling load for the long columns when the both the ends are hinged, and second when the one end is when one both the ends are fixed. Okay, now considering the case number 3, when one end is fixed and other end is free. One end is fixed and other end is free. Consider a column AB of length L whose one end of the column and B is fixed and other end A is free. A crippling load is applied at its free end of magnitude P. Due to this crippling load, column deflected to the point C. Okay, and the total displacement of the point A is delta. Consider Let us consider a section. Let us consider let us consider a section XX at a distance x from the point B. From the point B, and deflection or displacement of section is y. Okay, consider a section xx at a distance x where total displacement is y. Now, bending moment about this section xx, bending moment about this section xx due to the load will be equal to the, now what will be the perpendicular distance? Here the perpendicular distance of the load from the section is delta minus y, and this will produce a clockwise movement about the section. So taking clockwise movement as positive, load into perpendicular distance. Now, as we know that from the deflection equation, ei d2y over dx square is equal to the moment, and as we already determined, the bending moment about the section x-axis is p delta minus y. Now solve this equation. D2y over dx square is equal to the p into y plus p into is equal to p into delta. Now divide the whole equation by ei. D2y over dx square plus p upon ei into y is equal to the p upon ei into delta. This is a differential equation, and the solution of this differential equation is the solution of the above differential equation. Y will be equal to the C1 cos x under root p upon ei plus C2 sin x under root p upon ei plus delta. Okay, where C1 and C2 are constants of integration. Okay, now applying the end conditions for determining the values of these constants at point B, x is equal to 0, deflection is equal to the 0. Okay, now substituting these values in the above equation, 0 C1 cos 0 plus C2 sin 0 plus delta. From here C1 is equal to minus delta. Okay, and at point B, it means x is equal to 0. Slope is also equal to 0 because the B point is a fixed end. So slope and deflection both are 0 at this point. Now differentiate the equation dy by dx c1 dy by dx c1 under root p upon ei. Cos theta is minus sin theta. Sin x under root p upon ei plus c2 under root p upon ei cos x under root p upon ei. Now the dy by dx will be equal to the minus c1 under root p upon ei sin x under root p upon ei plus c2 under root p upon ei cos x under root p upon ei. Now substituting the values, dy by dx is 0, minus c1 is delta under root p upon ei sin 0 plus c2 under root p upon ei cos 0. Now from here c2 will be equal to the 0. Now putting the values of c1 and c2 in the equation, y is equal to minus delta cos x under root p upon ei plus delta. At a, x is equal to L, total deflection is delta. So delta will be is equal to minus delta cos x under root p upon ei plus delta, or cos will be L, cos L under root p upon ei is equal to 0. Cos theta is equal to 0 when theta is equal to the pi by 2, 3 pi by 2 and so on. Taking first value L under root p upon ei is equal to the pi by 2. Now from here under root p upon ei is equal to pi square by 4, sorry, is equal to pi by 2 into L, or p upon ei is equal to pi square upon 4L square, or p is equal to the pi square into ei upon 4L square. So this will be the crippling load for a column whose one end is fixed and the other end is free. Now considering the last case, case number 4, when one end is fixed and other end is free, and other end is hinged. is hinged. Now consider a column AB of length L, whose one end is fixed and other end is hinged. In that case, when a buckling load is applied at its hinge point, beam will deflect like this. Okay. Due to this buckling load and hinge joint, there will be a horizontal reaction is developed due to this buckling load. Okay. Now, again, let us consider a section XX at a distance x from the point B. Displacement or deflection about this section deflection about section is y. Then bending moment due to the load about this section will be equal to the moment generated by the load horizontal reaction will be, it will produce a clockwise moment about this section at that point C. So this will be equal to the force into perpendicular distance, and total distance from the point C AC will be L minus X. Load P will develop say anti-clockwise movement about the point C. So it will take negative moment and it is equal to minus Py. Okay. So total bending moment about the section will be H in bracket में L minus X minus Py. And as we know that the bending moment is equal to the EI d2y dx square if total deflection about this section is y. So it will be equal to HL minus X minus Py. EI d2y over dx square plus Py is equal to the HL minus X. The solution to above differential equation will be solution for above differential equation. Y is equal to the C1 cos x under root P upon EI plus C2 sin x under root P upon EI plus H by P L minus x. Convert this equation into d2y upon dx square plus P upon EI into y H upon P into P upon EI L minus x. Okay. So the solution of this differential equation will be y is equal to c1 cos x under root P upon EI plus c2 sin x under root P upon EI plus h by P L minus x. Where c1 and c2 are constants of integration. Okay. At point B, x is equal to 0, deflection is equal to 0. Okay. Substituting this value in above equation, y is equal to 0 at x is equal to 0, it means c1 cos 0 plus c2 sin 0 plus h by p into L. Cos 0 is 1, sin 0 is 0, then c1 will be equal to the minus h upon p into L. Okay. Now differentiate the equation about x dy by dx equal to the minus c1 under root p upon ei sin x upon under root p upon ei plus c2 under root p upon ei cos x under root p upon ei minus hp. Okay. Now at point B, x is equal to 0 and dy by dx equal to the also equal to 0 because B point is a fixed point. Now putting the values in above equation, 0 is equal to the C1 as sine 0 into under root P upon EI plus C2 under root P upon EI cos 0 minus H by P. Now from here C2 under root P upon EI is equal to H by P, or implies C2 will be equal to the H by P under root EI upon P. Okay. Substitute the value of C1 and C2 in equation. Y is equal to the minus HP cos x under root P upon EI minus HP, no sorry, plus HP under root EI upon P sin x under root P upon EI plus H upon P L minus x. At x is equal to L, y is equal to 0 because point A is a pin joint. Putting the value of these values in above equation. 0 minus h by p L, so this is L, cos L under root p upon ai plus h by p under root ei upon p sin बढ़िया h by p under root ei upon p sin L under root p upon ei plus h by p into 0. Now from here h by p L cos L under root p upon ei is equal to the h by p under root ei upon p sin L under root p upon ei or cos tan L under root p upon ei is equal to the L under root p upon ei. Tan theta is equal to theta when theta is equal to the 4.5 radians. So from here L under root p upon ei is equal to the 4.5 or p upon ei is equal to 4.5 square upon L square, or p is equal to 4.5 square upon L square into ei. This will be equal to the 2 pi square ei divided by L square. Now the buckling load for a long column having both the ends hinged, both the end hinged, equal to the pi square ei upon L square. And when the both the ends are fixed, buckling load will be equal to the 4 pi square EI upon L square. And when the one end fixed and other end is free, in that case the buckling load will be equal to the pi square EI upon 4 L square. And buckling load for one end fixed and other end free, other end hinged, equal to the 2 pi square EI upon L square. Now the equivalent length for the first case when the both the ends are hinged is equal to the actual length of the column. When both the ends are fixed, in that case the equivalent length will be equal to the half of the actual length. And for the one end fixed and other end free, in that case the equivalent length will be equal to the double of the actual length. And in the case of when one end is fixed and the other end is hinged, in that case it will be equal to the L by under root 2. Okay. Now remember this equivalent length. University. Now, now a built-up beam which is simply supported at its end, a built-up beam simply supported at its ends, compute its length given that when it is subjected to a load, compute its length given that when it is subjected to a load of 40 kilonewton, 40 kilonewton per meter length, it deflects 1 centimeter. Find out the safe load if this beam is used as a column with both ends fixed. Assume factor of safety is equal to the 4 and use modulus of elasticity is equal to 210 giganewton per meter square. Now the dimensions of the cross section of the beam is symmetrical I section having both the flanges are equal, dimensions of upper flange is 30 centimeter wide and 5 centimeter deep, and length of the middle flange is 100 centimeter and have 2 centimeter width. Now, a beam which is simply supported at its ends, okay, compute its length given that when it is subjected to a load of 40 kilonewton per meter length. 40 kilonewton per meter length subjected to a load, okay, and it deflects by 1 centimeter. So a uniformly distributed load is applying on the beam whose intensity is given W is equal to the 40 kilonewton per meter. Okay, so first of all we have to calculate the length of the beam for this given uniformly distributed load and for given cross section. As we know that the maximum deflection in the case of a simply supported beam having a uniformly distributed load about its whole length will be equal to the 5 upon 384 WL to the power 4 upon EI, where W is the uniformly distributed load, L is the length of the beam, E is the modulus of elasticity, and I is the moment of inertia of the cross section about its neutral axis. Here section is the symmetrical about the x-axis, so the moment of inertia can be easily determined by 1 by 12. Taken this section as a whole rectangular section and removing this section rectangular section from the this large rectangular section. So the we know that as we know that The moment of inertia of the rectangular cross section about its neutral axis will be equal to the BD cube by 12, where B is the width of the section and D is the depth of the section. So here, using this formula, the moment of inertia of this section is 30 into 110 to the power 3 minus 28 into 100 to the power 3 divided by 12. Now calculating this moment of inertia, I will be equal to the 99.41 into 10 to the power minus 4 in meter to the power 4. Now putting these value in the deflection equation of the deflection, delta will be equal to 305 upon 384 WL to the power 4 upon PI. Deflection is given 1 centimeter, so 0.01 meter is equal to the 5 upon 384 into 40. Length has been determined by, and moment of inertia is 99.41 into 10 to the power minus 4. Modulus of elasticity is 210 giganewton per meter square, 10 to the power 9. Now calculating, L will be is equal to the 14.15 meter. So the length of this uniform simply supported beam will be 14.15 meter, and this beam is used as a column whose both the ends are fixed. In that case, the crippling load will be equal to the P will be equal to the pi square EI into 4 upon L square. P will be equal to the pi square E is 210 into 10 to the power 9. I is equal to the 99.41 into 10 to the power minus 4 into 4 divided by the length of the column will be 14.15 to the power 2. So from here P will be equal to the 9330 kilonewton, and safe load will be equal to the maximum permissible load divided by factor of safety. So factor of safety has been given 4. So safe load will be equal to the 9330 divided by 4, 2332.5 kilonewton.